Hi, so today I want to finish this part and then I will talk a little bit about unconditional quantile regression, which is an alternative, and then probably I will have time to cover inference after model selection. First, generally, and then especially to apply to conditional and unconditional quantile treatment effects. I doubt I will have time for the last point, but maybe a few sentences. So if you take the main equation from yesterday, yeah, it works. Sorry. Main equation from yesterday is given here, where you have this unconditional distribution, which is an unconditional counterfactual distribution because it's not observable directly, but is built from a conditional distribution here for one particular population that you integrate over distribution of characteristics for the whole population. So what I want to add today is first that this conditional distribution may be estimated directly instead of going through quantile regression. Then I want to point out that you can also estimate that with reweighting, and that if you have, for instance, endogeneity, you may consider using, for instance, IV quantile regression to estimate that. So different details I would like to add. And after that, I want to compare with another approach suggested by Firpo, Fortin, and Lemieux that I call unconditional quantile regression, which is related but a little bit different. Okay, so first, distribution regression. We discussed that yesterday. Instead of estimating conditional quantile regressions to get conditional quantile function and invert it, we could directly estimate this conditional CDF, and because conditional CDF is a conditional expected value of a binary variable, indicator function y is less or equal than the threshold, then it makes sense to use a binary regression like a probit, a logit, coshit, or whatever link function you want. This is just a link function. And so it means for each threshold you can estimate one of these regression. You use just maximum likelihood estimation. You do separately estimation at each value, and then you very quickly get the estimated conditional distribution, and then you don't need to invert it or do anything else. You just plug in the previous formula. So it's very simple. It's quick. Does not need much new algorithm because these estimators are implemented. Maybe one interesting remark here is that actually the Cox proportional hazard model is a special case of this, where it imposes that the slope coefficients are constant. So there is the same relationship between the classical linear regression model, where you have an independent error term that implies that the slopes are the same over all quantile indexes, and the Cox and distribution regression, where Cox is an homogeneous distribution regression model, and distribution regression is more flexible because it's allowing for the fact that the effect of the variable is changing with the threshold. Okay? Something you cannot have with a Cox model. But beyond that, there is not much to say. It's very straightforward. So here a few comparisons. I mentioned a little bit that yesterday. Comparison between quantile regression, distribution regression. They are both flexible semi-parametric models because you have different, so it's still parametric, so here it's linear. Of course, you can see that as sieve approximation, but yeah, I mean, it's still a parametric model, but you estimate a different model at its threshold, so it's the added generality that you have here, which is similar in quantile and distribution regression. If you have fully saturated regressors, or if you have a non-parametric model, if you go in the direction of non-parametric, they are equivalent. Okay. If X is saturated, you get numerically identical results, so it does not matter if you go one way or the other, as it should be. But in general, they are different because they make different parametric assumptions. With quantile regression, you need a smooth, a continuous outcome. And like I said yesterday, if you do simulations, people tend to find that quantile regression is more precise than distribution regression if it's smooth. But there is no theorem here. It's more the result of some simulations And distribution regression is more flexible in the sense it allows for discrete outcomes or mixed outcomes where you have mass points and continuous points. But like I said, I think quantile regression is a little bit more natural because it has a special case, the classical linear regression model. Here, just to slide to say that this counterfactual distribution may be useful outside of treatment effect framework because you can use them in discrimination, like discrimination analysis where you want to decompose an observed difference, like here's a gender wage gap. So in such a case, you let D is 0 for men and 1 for women, and then what you are interested in is this counterfactual distribution that you would observe, for instance, if you put J equal to 0 and K equal to 1, you take the conditional distribution for the man and the distribution of the covariates for women. So what you are thinking here is about the distribution that we would observe if the characteristics of the woman were rewarded like the characteristics of the men are rewarded. Okay? And so the difference between what you observe for women and what you observe for women is a case where you have 1 and 1, so conditional distribution for women, distribution of characteristics for women. You compare this observed distribution for women with the counterfactual distribution, and you can call that discrimination in the sense that the characteristics are rewarded in a different way if you have a difference. While the difference between the same counterfactual and the observed distribution for men is explained by difference in characteristics. So it's, you can see that as a generalization of the famous Uraka blinder decomposition. You can do that for Quantile. It's probably more natural than for the CDF. But you can do that for any functional of the distribution. So like Quantile function or Lorentz curve or anything you want. And so, yeah, you see the link here between the treatment effect model, where this is, if D is a treatment, this is the treatment effect for the treated. Okay? While if you are in this case, in the decomposition analysis, this is the unexplained component and this is the explained component. Okay? So it's the same statistical object, so you can use the same method. Okay, this we have also already discussed yesterday. You can estimate exactly the same objects using reweighting. Right? So here it's example for the CDF of Y1 that you can obtain by reweighting. So, okay, so here if you don't divide, what you just have is, okay, so is a CDF for the treated, basically, okay, you just have to, okay, so you have to divide by the probability that D equal to 1 to get the CDF for the treated, but basically you get the CDF for the treated, and here what you are doing is that we are reweighting, so it's inverse probability weighting. This is a probability of being treated if you go back to the treatment effect framework. And using the conditional independence assumption and the observation rule, you can see that this will actually recover the distribution of Y1, the distribution of the treated outcome. And if you do the same with 1 minus D here and 1 minus probability D equal 1, you will get the distribution of Y0, and then you can inverse this to distribution to get the quantile treatment, unconditional quantile treatment effect. Okay, so this has been done quite early by Dinardo, Fortin, and Lemieux, but they did that for the density instead of doing for the CDF, and then later by Firpo, who did it for the quantiles, and he showed that actually the sample analog here with non-parametrically estimated propensity score attains the semi-parametric efficiency bound. Okay. And the semi-parametric efficiency bound is also attained by a regression estimator. If you use, you use something like that, and if you use a non-parametric estimator here, and then you take the average, you also attain the same semi-parametric efficiency bound. So it's completely parallel to the discussion that you have for average treatment effect. So one advantage of this approach here is that you need to estimate only one propensity score, While the other, you need to estimate the conditional distribution, so you need to estimate conditional function. A disadvantage, I would say, is that typically, depending on the application, but this propensity score is of less interesting, is a less interesting object from an economic perspective, while the conditional distribution of the outcome is maybe more interesting. So if you want to do like also study between, within inequality, you need a conditional model. But in principle, these are alternatives that can be used, and there is no clear statistical reason to use one or the other. Okay, I say that if you have an endogenous treatment, then you need to take the endogeneity into account when you estimate the conditional distribution. And so, for instance, instead of using quantile regression, you will use instrumental variable quantile regression. It's one possibility. So I already mentioned yesterday there are two approaches. One that is assuming rank similarities, Chernow-Zukov and Hansen. If you use this approach, actually you identify the conditional distribution for the whole population, so you can apply strictly the same, something like that. So to estimate here, you use IV quantile regression, then you invert it, and you plug in here, and you get, you can estimate the distribution of the potential outcome, even if the treatment is endogenous. While if you use the alternative approach by Abadian, and Imbens, what you will estimate is the CDF for the compliers only. And then to be coherent, you will need to take the integral with respect to the distribution of the covariates for the compliers, which is identified also. Okay. So otherwise, you are integrating a conditional distribution for complier over a distribution of covariates for the whole population. But I mean, if you assume homogeneity, it will work, but homogeneity here between compliers and always takers and never takers. Okay, so it's just a small remark. And here you can also work with reweighting in the IV setup. Okay, so maybe I go too fast or you are too tired. So I want to conclude this part by discussing. So if you should report conditional or unconditional quantile treatment effects. Because so now you have the tools to estimate both, like quantile regression, or you go over these counterfactual distributions, and then you get unconditional quantile treatment effects. So in terms of the ease of interpretation, I think that unconditional effects are easier in the sense that when people are interested in quantile effects, in some sense, they want to have the effect for the rich and the poor, or for the good students or the bad students. So depending on the outcome. Okay, so if the outcome is income, they want to see if the effect of the policy is the same for the rich and the poor. Okay? Now, if you report conditional quantile effects, you are reporting the effect for conditionally rich and conditionally poor. And I'm not sure it's what policymakers will have in mind when they think about rich and poor. Like, they have an absolute value in mind. Like, what's your income, period. They don't care if, given that you have a PhD, your income is relatively low, it's still much higher than most of the other people. Okay? So, by reporting conditional effects, you are not really providing what they are expecting. And actually, when you read papers, quite often people tend to interpret quantile regression results as if there were unconditional ranks, and there are actually conditional ranks. This actually is the most annoying example is if you have panel data with fixed effects. Let's say you are able to, you have a large number of time periods so that incidental parameter bias is not a problem. Then conditional quantile effects are conditional on your own fixed effect. So if each individual has a fixed effect. So actually the effect for high quantile are the effect for a good year of each individual and the effect of low quantile, effect of bad year for each individual if the time period is a year. Okay? So, which is very different from the effect for the rich and the poor. Okay? So, this is probably a good reason to report unconditional effects. At the same time, there is another way that quantile effect are a little bit misunderstood, or that as a researcher we tend to cheat a little bit, is that we interpret the effect for people at a given quantile. Okay? Like we say, okay, the individual at the bottom of the distribution, they have a negative effect, at the top they have a positive effect. But by doing that, we are implicitly making an additional assumption. We are assuming that the rank are not changing with the treatment. So we are assuming that if you take an individual I, the CDF, this is the rank of individual I if nobody is treated, and this is the rank of individual I if everybody is treated. We are assuming that they are equal. So like if you are at the top of the distribution without the treatment, you are still at the top with the treatment. If this is not true, then actually quantile treatment effects have no interpretation in terms of individual effects. If this is true, they have interpretation as individual effect. So to come back to the question of paper yesterday, if you have this assumption, then you can take the tau quantile of y1 given x, and you subtract the tau quantile of y0 given x. And because the same person is keeping the same rank, this is an individual effect. This is the effect for people who are exactly at the tau quantile. And now what you can do, you can actually calculate what is the distribution of this individual effect. Let's keep, maybe I should put given x equal a lowercase letter x, because I will integrate after that over it. Okay? So if you fix x, you have, if you fix tau, fix x, you have one value. If you fix x, but you consider all possible taus, you can actually get the distribution of these effects. Okay? So if you go from 0 to 1, you take the integral over tau, indicator function, this is less or equal than some cutoff, let's call lowercase letter q, and you take the integral over tau, what you get here is the probability that the individual effect evaluated at this particular x is less than q. For instance, if you take q equals 0, it will be the proportion of individuals that have a negative treatment effect for individuals which have this particular value of x. And now you can add a second integration over the distribution of x, and here what you get is what is the probability that an individual taken randomly from this population has a negative treatment effect. If you set q equal to 0, but you can consider all different values of q, and so you can have the full distribution of the individual effect. So it's actually a very powerful assumption, but with all powerful assumptions, it means they are very restrictive. So this is something to keep in mind. Actually, this CDF here, we can apply the same tool that we have seen yesterday to show that we can make inference about it exactly the same way that I have presented yesterday. Now, this rank invariant assumption is clearly more credible if you can condition x and if you have informative x's. And this assumption makes no sense for an unconditional quantile treatment effect. Because let's say, for instance, that the individual effects, the treatment effects are heterogeneous with respect to x. Okay? What will happen is that depending on your x, you will move in the unconditional distribution with the treatment. So you don't have the unconditional rank invariance. So in this sense, the unconditional quantile treatment effects, they should never be interpreted, from my point of view, as individual effects. Or, okay, maybe I went too far, but it's less credible. While if you can add x's, then you are comparing populations that are similar, And then it probably makes more sense to assume that. So in this sense, if you, okay, now this individual treatment, yeah, you have a question?
So I'm feeling it's might be exactly the same question I asked yesterday, but I'm still kind of puzzled by so we talked about the effect of a treatment on a low quantile, and saying it's different than the effect of a conventional on having a PhD or not having a PhD.
Yeah.
But in our linearly additive function, that effect is going to be the same. The beta tau is going to be the same whether or not the person has a PhD or not a PhD. So the conditional effect is the same for any condition, but it's not the same as the unconditional effect. And when I say it like that, it makes me very confused.
Okay. You can take, I think the best thing I have to do is generate data to show that they are different. But take the example where you have a linear model with d, x1, x2.
Yeah.
Okay. Now, if you do quantile regression only on d, you have this omitted variable. Now, I will come later. The omitted variable bias is weighted by the density. So it means even if d is independent of the other variable, maybe weighted by the density, it's not independent. It's not uncorrelated. And then you get an omitted variable bias, even with an independent covariate that is missing. Yeah, but okay, I will try to generate data to show you. I remember I did it like 10 years ago. I could not find cases where it was crazy, but it was clearly not the same.
Because it seems like, okay, I can understand, okay, so I remember what you were saying about that is this, that, yeah, well, if all this, the unexplained variation goes into the,
Yeah.
goes into the G when we don't include these things, just pick it up in the heterogeneity, but then go back to the point of being puzzled by the fact that when I do add in this conditioning variable, because of the additivity, regardless of what I'm conditioning on PhD or PhD, the coefficient on the treatment stays the same. And now it seems like maybe it should make us doubtful of the linear additive model for quantile regression.
No, okay, so I don't see it like that. I see it as you have to choose what you want. Okay. That is, you have effects that are indexed by the rank. And now a rank depends on your comparison set.
Yes.
Okay? So you may rank very highly in this room and not so highly in a room with different people.
Yeah.
And so it's natural that if you change the reference population, then you change the rank of the same person is at different rank.
That's fine, yeah.
And it's what you do if you do unconditional or conditional.
But then isn't it like an incredible coincidence that with different conditioning for PhD or PhD, I get the same effect of some other variable, but that effect's not the same as the unconditional effect?
I'm not sure I understood the question. Could you repeat?
Yeah, just...
okay, so, but we will see...
Okay.
So we will see one thing is that if you have an homogeneous quantile model, then the unconditional and quantile effect are the same. Okay, but which is not surprising. Okay, but maybe one equation that is coming could help. Okay. So yeah, but yeah, to conclude is that I think if you want to study, to get individual effect, you should go in the direction of conditional quantile treatment effects to be as informative as possible, which is especially useful for personalized inference, like if you want to target a treatment to people. But if you want to summarize the effect on the whole population, unconditional quantile treatment effects are probably easier to communicate. Okay, so now I go to an alternative way. I will explain the difference. I was surprised to see the number of citations because it's very well cited. It's a paper by Firpo, Fortin, and Lemieux, 2009. So think about, so here I did the binary treatment case. And for the binary treatment, it's quite clear that you want like to move either everyone from non-treated to treated, or you want to move the treated from non-treated to treated, something like that. Now let's say you have a continuous variable of interest. Think about education. And you want to report the effect of education on the unconditional distribution. One possibility is you have a clearly identified scenario. Okay? So let's say you decide to increase the minimal number of years of schooling. Okay? So now you have your population, 1x is education, some people are below this minimal level, so the artificial policy is they move above, and then you can calculate the effect on the unconditional distribution of this counterfactual change distribution of covariates. But in other cases, you don't have such a well-specified case. So what you can do is, for instance, you could increase education by 1 unit for everyone. Or, depending on the variable, I don't know, 1 standard deviation or 0.1 or whatever. And then you can get, okay, I have the effect of this counterfactual change in the distribution of the covariates on the unconditional distribution using this counterfactual framework. But, I mean, it means you must define this counterfactual change. An alternative is offered by Firpo, Fortin, and Lemieux in this unconditional quantile regression paper, where what they show how you can estimate the effect of a marginal increase in the value of the covariates. Okay? So if you define, so you consider a model completely general, where y is a function of the covariates and some unobservables u. And now what they want to do, they want to get the distribution of y when you increase the covariates by delta, which is arbitrarily small. So what they study is the effect of a marginal, so a small change, in the location, so it's a location shift in the distribution of the covariates. Okay? What if you add epsilon or delta here? What if you add delta to all covariates and to all observations? And then what they are interested in, they call it unconditional quantile regression, is the effect on the unconditional distribution of adding this delta to the covariates, okay, when delta converges to 0. Okay. So the advantage is that you don't need to define a counterfactual scenario. You can do it in a straightforward automatic way. Okay. And then what they show is that for continuous outcomes and covariates, this unconditional quantile regression at quantile tau can be written like that, and we should not be surprised. If you look at the second point, what you have is the average marginal effect on the CDF. Okay? So you have the CDF evaluated at the tau quantile, so tau is the quantile at which you want to estimate the effect. So if you increase x by epsilon or by delta, then the effect on the CDF will be equal to the derivative of the conditional CDF averages over all observations. So this is the effect on the CDF, but we want the effect on the quantile, and so you remember yesterday from the functional delta method example, the derivative of the inverse, you have to multiply with -1 over the density at the quantile of interest. So this is the effect on the CDF that you transform into the quantile by multiplying with this factor. Okay? And then you can estimate that by plugging in, you have to estimate this unconditional density and this conditional CDF, and then you take this is the average partial effect, and then you divide by the density at this quantile. Yeah, I can already say that one issue is this unconditional CDF, unconditional density function can be estimated only at the non-parametric rate, a one-dimensional non-parametric rate. So it means the estimator will converge more slowly than the previous one. And the reason is that because it's the effect of a small change, an arbitrarily small change in the distribution of the covariates. Yes?
So it seems this is a situation where you're shifting everybody's x value by a small delta,
yeah.
But you can perturb towards any other distribution of covariance x, right?
Yes, but then you get one effect for each variable. Because it's a marginal, so it does not, I don't know if I understood.
So like you have a distribution of x, and let's say there's some other distribution, and
Yes.
I could imagine defining that in a very similar way.
Yeah, you can define using other, so in other direction. It's, they do a small location shift, but you could think about other changes. And actually, there is recently a paper by Galvao, Antonio Galvao and co-authors where they consider changes in location and the scale. So, yeah, exactly.
I was just wondering if they discuss that in this paper, if you know.
They mention it a little bit, and then it's like more recently, like in this paper, is I think in Journal of Econometrics that they discuss more in detail this issue, because it's one restriction, okay, that it's a location shift, so it's an approximation to a location shift. Yeah. Okay, so this is one representation. Then there is another representation, which is no, I went in the wrong direction. Okay, it's here. If you define the conditional quantile treatment effect, which is what you get with quantile regression. So for instance, if you have a linear quantile regression model, this conditional quantile treatment effect will simply be the coefficient beta tau. Okay? So this conditional quantile treatment effect at quantile tau, in a linear quantile regression, just beta tau. Then you have this relationship between the unconditional and the conditional. So you see here is beta evaluated at this quantile. And what is this quantile? It's the conditional CDF evaluated at the unconditional quantile. And then it's an average of the different beta tau, and then weighted by the conditional density of y given x. So it's not a surprise, and maybe you see better with a figure, that if you have quantile regression, you have the different slope at different quantiles. You are interested in this the effect on the unconditional quantile. So for someone with x equal to x1, it's a 0.9 quantile that would matter. For someone with x equal to x2, it's a 0.8 quantile that would matter. And so the unconditional effect will be this average of all this slope. And they are weighted by the density. Why? Because if there is almost nobody here, it's clear that someone with x equal x1 will not influence much the unconditional median. For instance, if you go, let's say we go someone here, it will have no effect on the median, because even if you increase a little bit, it's still with probability 100% below the median, so it does not matter. Okay? So you have this link between the conditional and unconditional. Maybe can respond a little bit to your point that with the unconditional, so this would be the case, let's say if you include d and x, there is this link. So you also see that if this is homogeneous, then this is the same value. So if beta tau equal beta, then you take the average over constant and you get the constant. So if you are not too far from that, this little shifting will not matter much. Okay? Now, probably you can have pathological cases where beta tau is a very strong function of tau, and then you have to think about what could be the most extreme case. But it's clear that in such a case, you don't get the numerical equality. Yes?
So looking at the slide and then comparing it to the picture that you showed later,
Yeah?
the unconditional quantile regression is a weighted average of the conditional quantile treatment effects. And when you say weighted average, it's a weighted average across the different taus.
Okay. So for each value of x, there is only one tau that matter. And then it's a weighted average over the different value of x's. But different x imply different tau. So it's both at the same time, but in a mechanical way that go from x to tau. Okay.
And so when looking at this final display, when we have this linear QR model, I don't think I see in the notation the dependence between tau and x on the right-hand side.
Okay, so here it's beta evaluated at this quantile. This is a quantile. And so you see this quantile is changing with x because it's equal to the conditional CDF evaluated at the same. This is not changing with x, so we evaluate all of them at the same unconditional quantile, but we have to see that for some value of x's, you will get 0.9, for others 0.8, 0.5, 0.4, and so forth.
Okay, thank you.
Yes.
I have a more basic question about the quantile treatment effect, which is, like a few slides ago you mentioned, we don't want to overinterpret this, and
Yeah, I think it's a question of the assumption here. If you have rank invariance, then people don't change their rank. And then you can really say it's treatment for someone at this quantile. If people are changing the ranks, you should just interpret that as the effect on the aggregate distribution.
Okay.
So it's what people tend to say it's effect on the distribution or distribution of effect. To get distribution of effect, you need rank invariance. Effect on the distribution you always get, but it's just an effect on the population, if you want. It's not effect for someone in particular because we don't know the effect for someone in particular.
Okay. Cool. Thank you.
Yes.
In your relation between unconditional QR and treatment and conditional one, I was wondering if you make up the typical Simpson's paradox type of data,
Mm-hmm.
if there would be a way of finding a massive difference between
Okay.
conditional and unconditional effects. You know, like
Yeah, I see what you mean. I see what you mean. I will try to generate a massive effect to try to convince Guillaume. Thank you. Another question? Okay. So if not, maybe a comparison. If you have unconditional quantile regression, unconditional quantile treatment effect, in principle, they try to estimate something similar, effect on unconditional quantile function. Unconditional quantile regression is very simple you can do it in an automatic way, like you can apply some commands to all applications. Yeah, so you don't have to choose this counterfactual distribution of the covariates. Now, if the critique could be, first, it's the effect of a marginal shift, so only a small change. And there are actually many papers, many articles, where people use unconditional quantile regression and they extrapolate. Like they do an ORACA blinder decomposition using the coefficient from unconditional quantile regression. Personally, I think this is really misguided if the differences are big, because you have a small change and you extrapolate linearly, which is exactly what you should not do with quantiles. For instance, if you do that, okay, they call that Reef regression decomposition. If you do that, and let's say you have one category, let's say men, have higher variance of X than women. Because here what you're approximating is a small location shift. So actually, if the mean is the same, unconditional quantile regression will say the X's don't explain anything. Because actually there is no change in the mean between men and women. But for low quantiles, if you have higher variance of X, then it will have an effect on, let's say you have a positive slope on X, higher variance, then it means that you have lower values at the bottom of the distribution, higher value at the top of the distribution. So you will need to approximate also the change in the scale of the distribution of X. And then you will need, in principle, you will need to have all higher moments. So it's a good model for small changes, but not for big changes. Okay. And then I already say that in terms of estimation, it's a little bit slow because you have a non-parametric rate of convergence because of its density. Yes?
Going back to the first bullet point, so we say we're able to think about a counterfactual, but isn't the counterfactual a marginal change in the covariance? It feels like the margin is a counterfactual.
Okay, I agree. So you are saying that actually you also need to think about it. Is it? Yeah, okay. I agree. Let's say, obviously, I have worked on developing the other method because I think it's better, but I see that it's used a lot. So I'm trying to think about why it's attractive. And I think because it's straightforward to use. And then you are back in a linear model that people understand well. So you can report tables of coefficients exactly like you will do for quantile regression, but now it's about the unconditional quantiles. So I think it's attractive for this reason. Okay, so let's change quite completely topic. We have, yeah, great, 50 minutes. Inference after model selection. So it's, so I will first talk in general and then specialize to quantile regression. Probably most of you have heard of this general approach of double machine learning, double selection, but still I will explain that. I will try to stay intuitive. So the thing is that, so very often we have to make choices about the specification of the model because we don't know how the variable enter in the model. Let's say age, should we enter in a quadratic way, in a cubic way, in something else, or you have many variables, you don't know which one are important. So like the model specification is always a big problem when you have an application, when you get data. And so it's where machine learning methods are useful because they allow to do that in an automatic way. Okay. But the issue is that if you use an estimator, I will focus on lasso. If you use lasso to select a model, then inference after model selection, if you do it in a naive way, will not be valid. Okay. So because you are using the data to select the model and then to do inference as if you knew the model. Okay? So this is why we need methods to do inference after model selection. So let's start with model for the conditional mean, where I have y. I am interested in the coefficient alpha, which is the coefficient on D, so it's a treatment effect. And I need to control for variable z, and this variable z, they may enter non-linearly, so it's a partial linear model, and the error term is conditionally uncorrelated with D and Z. Now I have all these variables Z, and what I am doing, I will approximate this function G by a linear function, and I can do that by including many transformations of Z. Okay? So let's say you have age, and you will put age to the power 1 to 5, and then you will put indicator variables for different ranges, and you could have splines, you could have different things in this transformation here. So you end up with maybe 100 variables starting from 1. Okay? And in addition, you may already have many variables at the beginning. Okay? So this is the idea to approximate this G function that we don't know. This is just a nuisance parameter. These are nuisance parameters. We don't care about them, we care about alpha, and we'll make inference only about alpha. It's important because we are not able to inference about all these coefficients because the dimension, okay, maybe I should not say very strong things, but inference will be completely different if you want to think about other parameters. So now the fact that we try to approximate this function and we have potentially also many variables at the beginning means that the number of controls, the dimension of x, p, is possibly much larger than n. Okay? So think about very big data, but to make it possible, we assume approximate sparsity. It means the number of controls here that have non-zero coefficient s is small relative to n. But we allow p and s to increase with n. Okay? Especially p will be always larger than n. If p is fixed, it's fine. You don't have a problem. You can use OLS. But if p increases, you allow s to increase at some rate, you may have a problem, as we will see. Okay, let's actually go directly into the problem. I will try to give two intuition, or this is not very, it's more a formula than intuition, and then the second one will be more about intuition. So yeah.
So how do we get F? Do we choose it ourselves?
Yeah, but you can have a dictionary of changes that you can have many here. You can think, how do you want to approximate it, like you may see.
Seems like another researcher's choice.
Yeah, but it's more something that you can do before looking at the data. even the same for all applications, or more or less. I mean, before looking at the data, if you want to be flexible in age, probably having 20 transformation of age will do the job. So it's not that, okay, it will be a problem if you try with some transformation and say, oh, it does not work so well, and you try with a new transformation, then you are back to square one. But I think here it's credible that you can do that before looking at the data.
But the logic is that we want to throw as much as possible.
Yes. Okay. So think about a naive approach where you run lasso of y on d and x, and then you do OLS post lasso, where you regress y on d and only the selected regressors. Okay? And now the issue is the lasso estimator will actually not be square root n consistent, because it will converge, okay, under some assumption, but it will converge something like s square root log p divided by n. And so you see if p is increasing with n, s increasing with n, this will be slower than square root n. If it was square root n, like if p is fixed, you can actually use OLS with all the regressors asymptotically, and it will work. But here, if p increases with n, it will converge more slowly than 1 over square root n, and then we'll see in a few minutes, it causes a problem. So if you, in this case, you can write the estimated treatment effect, or you can estimate it using, so you take the residual when you regress y and x, well, think Frisch-Vaux theorem, and so I take this formula to think about what is the effect of using the estimated beta instead of the true beta. And here y, you can plug in the value from the model, and so you will have the part, okay, so what is done here is just, okay, you plug that here, so you have y d alpha x beta. Here you have some approximation error, but let's forget about the approximation error. Even without the approximation error, you get a problem. So you have d alpha x prime beta plus epsilon. You replace y with this expression. What you get is you have alpha di that you divide by the sum of d, so you get alpha, which is here. And then with epsilon, it's fine. Epsilon is a nice error term. So it's this as mean 0. Here you can apply a central limit theorem. So this will converge. Okay, this is converging distribution. We have multiplied with square root n, converges to a distribution. But then you have the problem with the estimated beta. And if you multiply with square root n, you multiply here with square root n, but beta hat converges more slowly than square root n, so this explodes. Okay? And so you cannot make inference because of that. Okay? So the naive approach will not work. Instead, one possibility, I will show two possibilities, double selection, double machine learning, and then apply both to quantile regression. One possibility is to do double selection. What is double selection? Is that you regress y on x using a lasso, and you regress also d on x using lasso, and then you do the OLS regression of y on d and the variables that have been selected either in the second or in the third bullet point. Okay? And actually this works. Why is it the case? Think omitted variable bias. You know the omitted variable bias. So if you have x, d, and y, you are interested in the effect. Here alpha, here you have beta, and now you have an omitted variable bias if there is a correlation here between these two. Okay? Think later it will be, it will be the opposite direction, but it will be theta. And so the omitted variable bias is a product of this covariance here, this effect here. It's not a causal effect, but this effect here times beta. Okay? So you will have a bias only when both are different from 0. Now, if you do the naive approach, you just regress y on d and x. If beta, for some x's, let's say beta is small, it's possible that lasso will miss this one, especially if it's in the square root n region close to 0. So this beta will be left out. But nothing prevents the corresponding theta to be large. And the omitted variable bias is a product of both. So if you miss this variable, then the omitted variable bias from this variable may still be large if theta is large, which compensates a small beta. Okay? While if you do both regressions, y on x and d on x, you make sure that at the same time beta and theta is small, so that their product will be very small. Now, if you do the simple, the naive approach, you need the estimator for beta to be square root n consistent. If you do the double selection approach, you need the estimator for beta to be n to the power minus 1/4, and theta to be n to the power minus 1/4, so that their product is square root 1 over square root n. So you can have estimators that are much less precise than what you need for the naive approach. Okay? So it's best see in this table. If you have the regression of y on x and d on x, and so you have pi and delta, and then you consider pi can be 0, small or large, and delta, okay, I have theta on the board, and beta and theta on the board. Here you have delta can be 0, small or large. So if you do only the regression of y on x, then you will capture large pi. You will capture these ones. But you will not capture variables, x's, that have a small pi, or sometimes you will not capture them, and a large delta. But these variables are still important because the product of these two is quite large. So the omitted variable is quite significant. And if you do selection in both directions, then you will capture these ones and that ones, and they are in the gray zone because sometimes we'll capture because of pi, sometimes because of delta, and sometimes not. But it can be shown that it does not prevent square root inconsistency of the estimator. Maybe a remark here is that the fact that you're... I see sometimes that then the estimator, if you do this double selection or double machine learning, it attains the semi-parametric efficiency bound, which gives the impression that you lose nothing by doing model selection. Actually, I think it's a little bit more complicated than that, because if you have, if you do this double selection, you will capture this last column and this last row. But variables that are here, in reality, you don't want to use them. They will increase the variance of the estimator. Because if a variable has an effect only on the treatment probability, but no effect on y, you would prefer to leave this variable out, because if you leave the variable out, you have more variation to exploit. So if we knew that this variable had a 0 effect on y, we would leave this variable out. If we could choose, we will take these two columns and we will leave this one out. It's not possible because we don't know, and it's why we are doing model selection. But I think it's a point that, that it's maybe keep thinking about, like doing the kitchen sink approach may not be so good if you have a variable that is only explaining the treatment probability and has no explanatory power on y. Okay, so now let's do the same for quantile regression. Yes?
So the omitted variable bias explanation is I think very compelling. When you're first talking about the problem in the expansion with where you do the series of the two terms, is there a way to see how the problem is resolved here?
Okay, I don't know why it's in a few slides.
Okay.
But maybe here you can interpret that as omitted variable bias. in the sense that if beta hat is not equal to beta, this part is still an omitted variable. If you want, you are omitting xi times beta minus beta hat, and if this is correlated with D, then you have a problem here.
And if the x's are also in the OLS part, do I recreate the right rate? Is that?
So if you do the double selection, if there is a correlation here, there will be capture, and so there will not be problematic. They will converge at the square root n rate.
That is not a
Yeah. Okay. Now quantile regression. The motivation was about omitted variable bias, and with quantile regression, we have also an omitted variable bias formula. Probably you have covered it. Did you cover this paper? Okay. So if you take the paper, Regression, Zukov, Fernandez-Val, they derive an omitted variable bias, which looks like the classical one. If you forget about that, you have the coefficient on the omitted variable. Okay, so here we should include x2, but we forget to include x2, and we want to study the effect on the coefficient on x1. And so this is the omitted variable bias for the coefficient x1. And so you have, as for OLS, the coefficient of x2. And then you have this covariance between x1 and x2. But what is new is you have some weights. I have not written the formula. But these weights depend on the density of y at the quantile of interest. What is more, and it's difficult to work with the weights they have in the paper. But here, there is another way to, so we can get a simplified formula if you want. Because we consider only small deviations from the true value. Okay. So the moment condition for quantile regression is written here. I mean, this is the moment condition for the coefficient x1. And so you have tau minus indicator function y is less or equal than the tau quantile. So this is 1 for x1 and 2 for x2. Multiply with x1. So if you take a small perturbation, so you have the true value and you perturbate it in the direction of beta tilde, and you take the derivative with respect to t, where you evaluate at 0, what you get is the expected value of the density of y at the quantile of interest, x1, x2 prime beta tilde. So you see that if you have small perturbations, these can be simplified, which is more complicated, can be simplified to the conditional density of y given x at the quantile of interest. And you can see that as an omitted variable bias. Okay. And so you see that in OLS you don't have this weight. So if you do like the double selection approach, but you do it where you regress D on X and Y on X, you will not have these weights, and maybe you will not include a variable that is important once you have the weight. Okay? So we want this omitted variable bias to be small, so we want to include all the variables that makes this omitted variable bias big. So, yeah, first just definition of the same model as before, but now for quantile. Okay? So we have the same model as before, but for quantile. Now we define this conditional density. It's the same as before, but now it's written with the error term. So if you evaluate at 0, it's the same as the density of y evaluated at the quantile. So this density is exactly the density that show up in this representation here of the omitted variable bias. What we will do, we will not regress D on X, but we will regress the density times D on the density times X. By doing that, we will make sure that the variables that have a high covariance, because now x1 is D, okay? So here this is general with x1, x2. Now we are interested in the coefficient on D, which plays the role of x1. So we want to make sure that this is small, so we run the regression of density times x1 on density times x2. And we will do that also with lasso. Okay? So, but here first, we define here the linear projection. Okay? It's just a definition of the linear projection. So the preliminary estimators, we will do double selection. We will use this lasso quantile regression or L1 penalized quantile regression. So we regress y on x using lasso quantile regression, and we regress the fi, so the density times d on the density times x using the traditional lasso. Okay? Because this, even if this binary, fi times d is no longer binary, I mean, the mass point at 0, but still it's a non-parametric approach if you want, so you can use a linear lasso regression. Okay. So you do these two steps, and you include the variable that are selected either in the first or in the second. Now you see there is this density, so you have first to estimate this density. But this density, or 1 over the density, it's possible to show that it's equal to the derivative of the quantile function with respect to tau. So if you change a little bit tau, if there is a big change, it means the density is low. If there is a small change, it means the density is small. So we have this representation. So what we do, we use a sample analog. So this is the derivative with respect to tau. So we estimate the density at tau plus h and tau minus h. Okay. So h is a bandwidth that must converge to 0. So the thing is here, what you are doing is you are estimating this conditional density to be able to plug in this regression here. Okay. So I come to the algorithm. First, we do lasso quantile regression of y on d and x. Second, we estimate the conditional density using 2 quantile regressions. Okay. So here you have 1 quantile regression at quantile tau. Then you have 2 at tau minus h, tau plus h, where you estimate the conditional density. Third, you can compute the lasso regression of f, estimated here, times d on f times x. And finally, you run a quantile regression, a normal one, of f times 1 on f times d, and f times x for all the regressors that have been selected either in the first or in the third step. And, okay, this is all coming from a paper in JASA by Belloni, Chanozukov, and Kato. And, yeah, I have a slide later with asymptotic distribution, but then they show it's root inconsistent, it's asymptotically normally distributed, and actually it attains also the semi-parametric efficiency bound for the given, the included regressor. And actually this density here means that it will attain semi-parametric efficiency bound. So it's weighted by the density. It's like the efficient GLS, if you want, in the OLS case. Okay, but so the thing is that you have to estimate it anyway, so why not plug it here in the final step? Okay, cool. Yes?
So with least squares regression, we kind of a quadratic or L2 objective with the L1 penalty. And for the quantile regression, they're both L1. Does that matter in any way? Or since we're just interested in rates, as long as it's like a good enough predictor, we're kind of happy with any type of regression?
Yeah. Okay, so I think people use L1 because then you have variables that are included and not included. Yeah. If you use L2 penalty, like ridge regression, yeah, they will all have some value of coefficients. Yeah. So you cannot do the simple last step. Okay, so I think it's the reason why people take L1 penalty. Actually, I find it's maybe more surprising to have an L1 penalty when we are, but yeah, it's just a device to select the variables that are relevant. But there are papers showing that it works. I mean, it's similar properties as the lasso regression.
Yeah. Okay. Yeah. I mean, it's both like kind of satisfying and unsatisfying in the sense that it doesn't give you a great way to distinguish between different regularization techniques. So I guess anything works, but
yeah. I see. I mean, here it's a different way to shrink the coefficient. And I mean, here I'm presenting with lasso, but in principle you can use other stuff. I mean, random forest, neural network.
So I guess the comment is just a general.
So yeah, it's.
How do we choose if they're all?
Actually, these are more. they can even be black boxes satisfying some regularity conditions.
You want to be able to do this without selection per se, or is that the...
I think I was just wondering how we choose between different selection and regularization methods in practice because they all kind of have similar asymptotic areas.
And if we're estimating the F hat with the quantile regression tree,
Yeah.
is the quantile regression to be correctly defined in the theory?
Yes, I guess so. Yeah, it's a derivative of the true quantile function. But here, like, you don't need the double selection step at this point because if you have a variable that has a small effect on the quantile function but a big effect on D, for the density it doesn't matter. So, and I mean, they are just weights. I mean, I'm not sure you, yeah. So, I'm actually like if you have homogeneity, you don't need the weights. Okay. But yeah, to be clean, the idea is to start from where is it? From this formula, we want that to be small, and then it's same. So it's why we plug in this density. Okay, so let's see another approach, and now I go back to model for the mean, okay, and then I will do the thing with quantile regression. So this is called double machine learning. In several papers by Chenodukov and many co-authors. So the idea is actually similar, okay? But then I can show you the formula you wanted. So the idea is you regress y on D and, so, no, you regress y on x, and you regress D on x, and then you do the regression of the residual of the first and the residual of the second. Think Frisch-Vaux theorem. So actually, if you use, let's say you have finite dimensional, you have small dimensional x, and you do that with all the regressor, with OLS, here again, you get numerically the OLS coefficient, you know that. So here, because its dimension of x may be larger than the number of observations, we do that with lasso and with lasso, and so you don't get numerically something that you could get in one step. But so the idea is, so then this is the regression of these residuals on that residuals. And on the next slide, I can show you what's the idea. The idea is, if you take here this representation and you plug here the value, you plug instead of v hat, you plug that, and instead of u hat, you plug the other one. Then you can split in 3 parts. Okay? Like the first one is the same as before, is a nice one, converge. Okay. Now the second one is a difference with before, is that we have the product of the estimation error. Estimation error when you regress d on x, estimation error when you regress y on x. So the fact that we are multiplying these two regressors means that we get the product of the estimation errors. So you see that what you need is only that this product is square root n consistent, which means that it's enough that each of them is n to the power minus 1/4 consistent. And then it will vanish. And the third one is, with lasso is not so problematic, it will also vanish under some assumption about the number of, here you have the assumption about approximate sparsity, which is S cannot increase too fast. Okay? But it can increase with n. Okay? And then it follows that what dominates is the first part, and you get an asymptotic normal distribution with a standard, completely standard asymptotic variance covariance matrix that can easily be estimated. Now, if you think about the moment condition, Or if you think about the approaches you could take, first naive approach would be you do only the regression of y and x. Okay? So this is the first approach. Second approach is you do only the naive propensity score adjustment. So in this first approach, which is the first thing I mentioned at the beginning, if you miss a variable that has a low beta, but has a high correlation with D, then you will have a bias. In the second one, if you miss a variable that has a low correlation with D, but a big effect on Y, you will get a bias. While in the third one, where you have both regression, so you have the double selection, or double machine learning, because you use machine learning to estimate that, then you have the product of the estimation errors, and then you can get a square root n consistent estimator. And Chernozhukov and co-authors, they call that Niemann orthogonality. And formally what it means is that the derivative of the moment function that you are using with respect to all nuisance parameters is equal to 0. So here the nuisance parameters are beta and delta. And the thing is, here, if, let's say, you estimate badly beta, it's not a problem as long as you have the correct delta. And if you estimate badly delta, it's not a problem as long as you have the correct beta. Like 20 years ago, we would say it's a doubly robust estimator. Okay? So people were saying you can use two parametric models. If you misspecified one, it's not a problem because the other will make the estimation consistent. Here we are doing that in order to have a product of rate of convergence. And so this property is called Niemann orthogonality. Now if you want to do that for quantile regression, what we need to do, so the normal moment for quantile regression, you have this indicator function minus tau. Okay, so here you have the regression. And if you just have D here, you forget about that. You just have D, you have classical quantile regression. If you just do the regression of Y on D and X, for instance, with lasso. But if you do that, if you don't have that, you have the same as the first moment on the previous slide. It's not Niemann orthogonal. While here, we are multiplying. Here we have DI, we have the same idea. The only difference is we multiply with the density. So if you compare here, the third one, which is Niemann orthogonal, if you do the same for quantile in a mechanical way, you don't add the density, but because you know that this density matters in the asymptotic distribution, you plug it here. And then you see if you estimate, you have an estimation error in beta, take derivative with respect to beta, but delta is equal to the true value, or theta is equal to the true value, then the derivative of the expected value is equal to 0. And if you do the same with respect to theta, but you evaluate a true beta, the derivative is equal to 0. So this is a Niemann orthogonal moment condition. And so you can base an estimator on that. And so here is the algorithm. It's also in the same JASA paper. In the algorithm, first you do a lasso quantile regression of Y on D and X. Then second, they do a post-lasso quantile regression. I'm not sure why they need to do that, but it's what they do. Third, they estimate this conditional density. Fourth, they compute the delta here by doing the same regression as before, regress f times d on f times x. And then they construct the score function. That is, they take the moment here and they plug in the estimated theta, the estimated beta. This is an approximation error that they assume to be small. Okay? So it means this is also part of the approximate sparsity assumption. That is, if you let S go a little bit, not too much, but a little bit, then we are assuming that this approximation error is small enough. Okay? It's basically an assumption. Okay? And so once we have plugged in this value, the only remaining parameter is alpha. So we estimate alpha by solving this moment condition, and it's the last step. Okay? So, but this is similar to what they do for average effect. Okay. Yeah, okay, so the last slide about here are asymptotic results, and I mean, the proofs are very long, but then what they show is that everything is fine, square root and consistent, semi-parametrically efficient, asymptotically normally distributed, and in theory, it's very easy to estimate this asymptotic variance because you have already estimated this density, then we can just plug in, but it works not so well. If you just plug in here, it does not work so well because this is assuming efficiency, okay? Because we have weighting with the density, so we don't get the sandwich formula because you have estimated with the density. But actually, in simulation, it works better if you use a robust one, even if in theory it's efficient. So they compare different estimators here. Yeah, so you should look at this paper for the details. But so what I have shown is that for conditional quantile treatment effects, you can apply the method that have been suggested for the partial linear regression model. It is double selection or double machine learning, but keep in mind that the omitted variable bias is density weighted, and so you have to estimate this density and plug it in the different expressions. And finally, what about the unconditional quantile treatment effect? This will be much shorter because it's a special case of the unconditional average effect, as was briefly mentioned yesterday. So if now you are interested in unconditional, I start with average effect, and then we see with a very small variation, we get a distribution. So this is assuming conditional independence assumption. Okay. And we first define the regression function. Okay. G dx is expected value of yd given x, which can be estimated with conditional independence assumption with the expected value of y given x and d equal lowercase letter d. And here you have the propensity score, probability of being treated given x. And you know that you have three different approaches. A regression approach, where you can get the unconditional expected value of yd by taking law of iterative expectation, the expected value of the conditional expected value. This is the regression approach. Or you can have a propensity score reweighting approach, inverse probability weighting, where you reweight with the probability that d is equal to d. So here we do that for 1d, but you can do the same for the other. And finally, you have the doubly robust approach, if you want, or it's inverse probability weighted augmented regression, where you have at the same time the mean, the conditional expected value, and the reweighting. And here again, you can see it's doubly robust in the sense that if you misspecify, let's say, the g function, this one will cancel out with this indicator that on average will be equal to the denominator times minus g will cancel out, and you will go back to the second line, which is fine. Or if you misspecified md, then it does not matter because this one will be 0 for each x. So this will cancel out, and you will go back to the first one. So it's another way to say that it's Niemann orthogonal, the third one, while the other two are not Niemann orthogonal. Okay? So it means if you have a correctly specified model, if you have a parametric model, you can use all approaches, regression, inverse probability weighting, or doubly robust. But if you are using some machine learning like lasso to estimate, to select a variable of interest, it's only the third one that will work because it's Niemann orthogonal. Okay. Yes. Now, if you want interested in quantiles, well, you can do everything the same, except that you replace y with the indicator function y is less or equal than y. And then you get the CDF at 1y. You can do at all values of y, you get the full unconditional CDF that you can invert to get the unconditional quantile function. So in principle here, you don't need anything different. And in the same paper, so it's Belloni, Cianuzzuca, Fernandez, Valhansen, in Econometrica, they cover both average treatment effect, quantile treatment effect, and also IV for average treatment effect and IV for quantile treatment effect. You just to add a denominator for IV. So yeah, so here this part is very similar. if you are interested in average effects or quantile effects. While for conditional, it's more complicated. You have to estimate its density. And I'm not so sure many people will use that, and I'm not so sure it works very well in finite samples. Okay? It's maybe a curiosity more than something very practical. We will see, but I'm not very hopeful because estimating this conditional density is not easy. And we already knew about efficient quantile regression and nobody used it. There is also the problem with misspecification. But here it's non-parametric, it's not a problem. But yeah, it is for quantile regression. People don't want to use weights because if you misspecify the model, you don't know what you're estimating. I don't know if you have a question about that. Yes?
It's about the density that you use
Yes.
to weight that. It's related to Young's question, but so if you are in a high-dimensional setting, like so you need to do this selection procedure before estimating the density. So maybe that's what you showed, but I was just not sure up to what point it will. You can do this actually.
Okay. Thing is, you can you can use quantile lasso to estimate these two conditional quantiles. So you don't need several steps here. You can get one quantile regression, L1 penalized quantile regression, evaluated at quantile tau plus h, and one evaluated tau minus h. And you get these values for each, these two fitted values for each observation, and then you get this density for each observation. So I would say this is not so problematic, but still, you have to choose h. Then what will happen is you will have observations where this is negative. You have observation where this is very close to 0. You will take different h and you will get different results. There are all this sort of stuff that makes it not attractive. So I agree with the general message. Computationally, I don't think it's a big deal.
There's no proof of selection consistency under specific condition.
I don't understand the question. I mean, the lasso quantile will be consistent for that.
Okay, it will be consistent for that.
Yes. We don't make inference about that. Okay, so it's like a nuisance parameter which is consistently estimated.
Okay.
Yes.
So we have two questions. One going back to the whole machine learning part of the lecture. I think I'm a little bit confused on the distinction between the term Neiman orthogonality and doubly robust. Could you?
Yeah. From my perspective, it's the same thing, so it's why you are confused. But maybe I am confused. I think doubly robust is coming from an older literature, okay, with a different goal, which was, let's use a parametric model for one, parametric model for the other, and one of the two will be right. This Neiman orthogonality is you have nuisance parameters, and if you have small deviations of the nuisance parameters while keeping the other at the true value, then derivative is 0, the effect is 0. So which means the effect will be small, and this is the formal definition of Neiman orthogonality.
And then the second question I wanted to ask was, I think I missed the answer to Guillaume's question about the slide. For this pointer result to hold true, do we need the quantile function to be well specified?
Yes?
In which case, if we take a look at the weighted variable bias formula that we have,
Mm-hmm.
it just feels a bit incongruous that we were using this small VB formula to avoid the weights, but if we're well specified, then those weights, don't they simplify to something nice? Or
Okay. Are you talking to that? Or are you are making a link between the omitted variable formula and that? Is it right?
I think so.
Yeah. Okay. Then, because it's omitted variable formula is not for this conditional quantile function. I mean, it's for the estimated treatment effect, okay, for the estimated alpha. And here we are estimating something different. And we are not making inference about that. I'm not saying that this is asymptotically normal, that we can make inference about that. We cannot. Okay. But we can still consistently estimate this conditional density. So, really, here we can make inference only about a scalar parameter. Okay. So, we cannot make inference about beta. Okay. And the dimension of beta, we allow it to increase with n. We are targeting the inference to alpha. Okay. So, we are choosing one coefficient that is of interest, and we want to make inference about this coefficient. And because we do that, we can use a double selection or double machine learning approach. If you are interested, let's say there is another variable in Z that you are interested in, then we will do differently the estimation, because then one step will be the same, but the other will be, we will regress this particular variable in Z on all the other. And so we will use a different set of covariates because we will target a different parameter. But in all cases, it's just a scalar parameter that we are targeting, and so we are designing the whole procedure for this particular parameter.
So I think I follow that.
Okay.
If you don't mind going to the slide where you showed us the Angers-Schutz-Bell, Fernandez-Bell result.
Yes.
I think my question is about that we came up with a simpler expression from the motor condition.
Yeah.
And thought of that as like the small OVP formula,
Mm-hmm.
and use that to motivate why we need to figure out what this F is.
Yes.
But the way we figured out this F was by using a result that holds true in the well-specified case.
Okay.
But then in the
Yeah.
well-specified
Yeah.
case, what would that mean for the
But yeah. But here, the way we see that is we are non-parametrically approximating the G function. So in this sense, you are well specified. So and it's why we are consistent when we estimate F. So we cannot use a small model because then we'll be biased. But, okay. Yeah, 1 minute. So yeah, I will stop. I had prepared a few slides about another paper. Just one sentence why I wanted to talk about this other paper is what is interesting if you have quantile regression is that you are specifying the whole conditional distribution. And you can use this conditional distribution like you would use a likelihood, for instance. So you can generate observations. So if you have a well-specified model, you can really generate observations. And so if you estimate the model, you can take the model, generate observations, and basically look if they fit with the true data. And if they don't, it means you have the wrong parameter, and you iterate. And it's basically what they do. In a panel context, what they do is that they parameterize the individual effect. So these are the individual effects. And they parameterize the outcome given the individual effect. They enter here. And then they estimate this model sequentially until they converge. Okay. And it's why I like this approach. And this is something that can work in different ways. They have other papers. The sample selection paper of Arlan and Bonham is also similar. They use the fact that if you have all conditional quantiles, you have the whole distribution, and then you can estimate from the copula between this, the rank in the outcome equation and the rank, or the probability in this, the latent rank in the selection equation. So you have additional difficulties with quantile models, but you have also advantages. And one of them is that you can then treat the estimated model like a likelihood model from which you can generate data and do things you cannot do if you only specify the conditional expected value or something like that. Okay, so it's finished. So I will not be teaching in the next 2 days, but I will still be attend the lecture. So if you want to talk about anything about the course or your research or whatever, it will be a pleasure to talk to you tomorrow or the day after. Okay. Wish you a nice evening.